Atomic absorption spectroscopy. Okay, so this technique we use to analyze, like, spectroscopy's interaction between what and what again, Alyssa? Light and matter. So atomic absorption spectroscopy, what matter are we talking about? Melissa? What matter? What matter? Where's my pen? Yeah. Now it works. Say it. Atoms. 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 So this only works for atoms. Well, what the heck could you be analyzing? That's an atom. Are we always interested in molecules? What the heck? Andrew, what the heck do you analyze that's an atom? Is there anything? Sodium. Calcium. Yeah, carbon would be great, but this won't work for it.
Not sure.
This won't work for it.
Metals?
Metals is really what we're after, because that's what's going to exist as atoms in nature. Now, in solution, there'll probably be ions, right? So that's going to be a problem, and we're going to have to fix it. We're going to have to make those ions atoms, and then we can use atomic absorption spectroscopy. And we're going to see that atoms, just like molecules, they absorb and they can emit, but it's not going to be wide spectra at all. These are going to be really, really narrow. They're going to be lines. That's what we're going to see. So at room temperature, Brandy, in a dilute solution of sodium and chloride, the sodium and chloride ions are in their blank state. Ground state, yep. Okay. So when a dilute sodium chloride solution is placed in a flame, the flame turns orange. Why? You seen this? This is one Gen Chem lab that I miss, man. I had a lot of fun doing this. You get all these metals, right? And then you put them in water. Then you have to get the little wire that I was bothering Andy with, right? Oh, I need my flame. Right? We don't do this lab here, I don't think. Is this even on? Maybe it is. Oh yeah, it's there. Where's my little... Ooh. It's too much. Let's start with everything closed. It's easier. I was trying to get lazy. Remember the rules? Start with everything closed, and life is easier. Supposedly. Maybe this is the one that doesn't work. I smell it though, don't you? There it goes. Jiminy crickets. Let me adjust this guy, get our nice, give it some air. Okay. We'll talk about flames coming up here, but the idea is there's a little loop on the end of the wire, right? You dip it in the solution, and you just put it in the flame, and it's orange. Now, why is it orange? Someone was saying something. What goes? So the sodium atoms, right? They're in their ground state, but the temperature of the flame does what to some of those atoms? Gets them into their excited state, and then to get back to the ground state, they what? Are they emitting or absorbing? emitting. They're emitting orange light. Okay. So, I got it fixed. We got to go on our little field trip. Come on, let's go look at our discharge lamps. All right. We're going to place atoms. We're going to have a hot gaseous medium, and we're going to apply a high voltage across them. And let's go take a look at it. And we'll lock the door. I don't think we're going to go that long. I'm going to show you this too. We're going to go into where the mass balances are. So why do these hot gaseous atoms produce line spectra? Well, they're atoms, right? So that's what atoms will do. Let's see if we can just bring this out a little bit better. Atomic line widths. Sketch a general absorption spectrum of a solution containing molecules. So I'll have my x and y axes. Andy, what will be on my, what's the name of the axes, of the x and y axes for a general absorption spectrum? Absorption and the x-axis? Wavelength. No. Right? Because if you go up to the UV vis and you get an absorbance spectrum, you've got y-axis is your signal, which is absorbance, and then you have all these little nanometers on the x-axis. So it'll be, you can write a little symbol if you're lazy for wavelength, or you can write nanometers, or you can write the word wavelength. All that will work. All that will work. And then we're supposed to sketch it. All right, just sketch some blob thing, right? Okay. It's going to be broad, and it's going to cover a range of wavelengths. Sketch a general absorption spectrum of a gaseous atom. Okay, so if we could do this, you put it in the UV vis. My axis labels will be what again? Y-axis is absorbance, wavelength, or nanometers or something. Okay. And then the absorption spectrum, you would draw what? Just well, lines, but you kind of draw a little bit of a base on these guys, a little bit wider on the bottom. You can draw as many as you'd like, but the point is that it's really narrow, but a little bit thicker on the bottom. It kind of goes out on the bottom, right? There's a little bit of width there. I'm kind of exaggerating that, but that's the idea. Atomic spectra resemble lines, but they do have some narrow width, right? It's not just a single wavelength. There is some width there. Okay, and it's due to 3 reasons. The first one, uncertainty principle broadening. Okay, P. Kimmer, what are they talking about? Uncertainty principle broadening. What was that? There's the name of a guy. This is his principle. Starts with an H. Heisenberg uncertainty principle, right? And the idea there was kind of what? The more you had an idea of for example, position of an atom, the less you had an idea of its energy or momentum. And it's kind of this game you're playing. If you want to nail down the energy and get a really strong measurement of it, then you have no idea about its position. And it's kind of just getting into the idea that those energies, they're not always what they're supposed to be. There's this uncertainty principle. There's this range that you just can't control. It's this inherent property of nature. You'd like to say that energy is 68.2009876 kilojoules. No, there's this Heisenberg, so you can't nail down the energy of these things that well. Okay, and then inside the lamp itself, there's Doppler broadening. Doppler broadening. You've heard of Doppler radar, maybe? With the weather. You don't want this to happen, but it could someday. You're stuck out on the interstate. Maybe make it safer. You're on a rural road. Okay? You're on a rural road, and a train could be approaching you, right? Or an ambulance is going to fly by you, right? And both these guys have their little horns going. What happens to the pitch? The guy pushing the button on the horn, he doesn't hear any difference. But you sitting there as that horn approaches you and flies by you, do you hear the same pitch the whole time? No. Go to a racetrack. That's a really good example. Right? Well, that's kind of its sound intensity, but it's also Doppler. So all it is sound, does sound have a wavelength? Yeah, it's kind of like saying, does sound have a frequency? Yeah, there's different frequencies, higher frequencies, shorter wavelengths, so it's kind of synonymous. So as this object is approaching you, those waves get compressed, or the wavelength shortens. That means the frequency gets higher. So that means a pitch that sounds higher, right? And it's going away from, so once it gets past you, now, right, as it emits that wavelength, as it emits that sound, it gets spaced out further. So the frequency gets shorter, the sound intensity is always dropping because you're going away from it, but the frequency goes down, right? So you can hear that by this. Let's see here. Get it on a sound that you can hear. You can definitely hear that, right? So as long as I'm not moving it, you hear the same frequency all the time, right? But then I start moving it, look what happens. Or I could swing it around and hit Andrew in the head. All right, you should really hear a difference there. So even though this thing the entire time read 5.49 kilohertz, it's the Doppler broadening. So what does that have to do with atomic spectra resembling lines? Well, let's say instead of absorption, it's easier to think of it as emission, I think. Well, it could be absorption too, but let's think of this plot as emission. Because you just observed that, right? You just looked at those lamps and you saw the lines. Okay, so what's doing the emitting? Those hot gaseous atoms in that lamp. Well, are all of them staying put, or are they moving inside there? They're definitely moving. So the ones that are moving towards you when they emitted their light are going to emit a little bit Doppler shifted frequency. Though if they're moving away from you, they're going to emit a red shifted Doppler shifted, right? A Doppler frequency, right? That's where the idea of red shift, blue shift comes from. If this emitter is moving towards you, boom, right? Its frequency is going to be a little bit higher, so that would be a blue shift or a red shift? Blue shift, because blue is a higher frequency than red. That's the idea, right? So if it's going away from you, it's a red shift. So it makes sense with colors, but they also use those words for sound, okay? That blue shift and red shift.
So it's just like...
So even though it should be a single energy, like you like to write out those energy levels,
yeah,
all right? There's the energy, and here's the energy levels. It's quantized because they're atoms, and it jumps from this excited state all the way to the ground state, emits a photon. It should be one single frequency, one single wavelength, but since it's moving, it's Doppler shifted, depending on whether it's moving towards you or away from you. So that results in a little range of frequencies that you're going to observe. That gives rise to the line width. It's not going to be just that one single wavelength, that one single energy. So it's a big contributor, this Doppler broadening. Just like the Heisenberg uncertainty principle, saying that these energies, right, look at that. Just by drawing a line, we're breaking the rule on the Heisenberg uncertainty principle. You can't be saying that. It's going to be a range, so maybe make your lines a little bit thicker. All right? And if you really want to do it right, you'd make it thicker, thickest in the center probably, because there might be some most likely energy, and a little bit lesser on the ends. It's complicated. It's not a fixed energy, Heisenberg uncertainty principle. Okay? Doppler broadening. The frequency depends on whether the emitter is going towards you or away from you. Or if it's absorbing, depends on whether the absorber is going towards or away from the incoming light. And then there's pressure broadening. If, again, the problem is you got this lamp, and these these atoms hit each other. Well, if they hit each other, they end up changing their energy levels a little bit. They call that pressure broadening. Okay. They could also have self-absorption. One emitter emits the light emitted from another atom. Okay. So having high pressure in those lamps is not a good thing either. That'll mess up and make the lines wider. So those three contributions to the line width of a absorption or emission line make sense? You could put those in your own words. Andy, could you do that?
I'll try.
Which one would you looks the ugliest? Which one do you want me to go over another one? Want me to go over it again?
So Doppler broadening is moving towards you. The lines are getting.
Now instead of the it, say the molecule or the atom, the emitter. If you're talking about the emitter or the atom.
The atom is the atom is moving away from you. It's getting higher.
Yeah, if the atom's moving away from you and it emits light, it's going to be redshifted. The light would be redshifted.
And it's moving towards you, it would be
Blue shifted.
which means it's going to be higher.
A higher frequency. It's going to look more blue, have a bluer tinge. Yeah. So that's the Doppler idea. The uncertainty principle is just, you can pretty much just say it's you can't measure these exact energies. There's an inherent uncertainty in these energy levels. Even though they're supposed to be energies quantized, well, those quantized energy levels themselves, you can't exactly measure them that well. Okay, there's a complicated game that's been going on there with the Heisenberg uncertainty principle. You could just call it Heisenberg uncertainty principle, be done with it. There's not really much that I'm going to ask you to explain. I'll just ask you to name the three. Okay, pretty much. Okay. Atomic absorption versus atomic emission. So, right, we've got these lines. Upstairs, when you did the AA, you were doing absorption, right? You had, if you're looking for sodium, you had sodium light going through the flame, and if there are any sodium atoms in the flame, they absorb the light, so you can get absorbance signal. Well, we could have shut off that lamp, the sodium lamp, and looked for sodium light and done emission spectroscopy. Okay? So that's what we're talking about, absorption versus emission spectroscopy. Fact, atomic absorption spectroscopy works with a very large population of atoms in the ground state. Because Brandy already said that. In fact, at the temperature of the flame, 99.9% of all atoms are in their ground state. So you've got a lot of atoms to work with, right? Because if you're doing absorption spectroscopy, look at all the guys that can absorb. Atomic emission, however, works with a very small portion. Only 0.017% typically of the atoms are in their excited state. So you'd have to get that flame a heck of a lot hotter if you want to bump that number up. But all we're working with is 0.017%. Which method do you think is the most sensitive technique for quantitating metals? Atomic emission or atomic absorption? What would you guess?
Sensitive meaning like?
Meaning take a really dinky amount of sodium. This technique can measure it, whereas the other technique could not. That's what I mean by sensitive.
Absorption.
So with all these words, you're supposed to say absorption, right? Because you've got this huge population of the ground state to work with. But then, that's where we go into the room and we do the little demonstration that I showed you. We had case 1 and we had case 2. Case 1 was just putting a yellow filter in front of a lamp, a flashlight, and seeing the change in intensity, right? Case 2 was having the flashlight off and then seeing a little bit of light. Which case was which? Which one was absorption? Which one was the emission process?
Absorption of the black. The black.
The second one.
Absorption, the darker one. Because less light was being emitted to it.
Yeah, well, they're both. You can argue for absorption in both of them, really, because the filters are absorbing. So you can argue for absorption in both of them. The point of that demonstration was to show you background. which case had a really bright background? The first one. Okay, so now talk about absorption and emission spectroscopy. Which one of those has a really bright background?
So the first one was absorption because it was absorbing everywhere but yellow.
Well, think of any absorption, all those instruments, those flow diagrams, and how the whole thing works. Which does that have a really bright background or a really dark background? Absorption. Absorption always has this incident intensity, and then maybe a little bit gets attenuated, and you measure what gets transmitted. Emission spectroscopy, you've got a black box, and you try to see light. That's emission spectroscopy. When we did case 1, I was shining that bright light. I should have been shining it in your face, maybe, right? It's really bright. And then you try to measure a small change in intensity with that yellow filter. Now, yeah, it was really easy to see, but I could have put in a much lighter yellow color. And your eye has to detect the change in intensity. That is absorption or emission.
Emission.
Which one is it? You want to detect the change in intensity. Isn't that a change in intensity? Right? You have to measure absorption. You got to measure the incident intensity, and then you have to measure the transmitted intensity. And your incident intensity, is it always brighter than your transmitted? Yeah. So absorption or emission, which one has a really bright background? Absorption. Because the more intense that, right, the better your measurement's going here. But that's really hard to do. Because look at the background for emission spectroscopy. Is there a background? No, everything was off. And all you had to see was just that little prick of light. And you could detect it. Your eye could detect it. So emission spectroscopy is inherently built to be sensitive because it's just looking for just a little prick of light in a background. So this 0.017%, who cares? This is a ridiculous amount. You don't even need this much. You can go much, much lower with emission spectroscopy. So emission spectroscopy is definitely a much more sensitive technique. Whether you're talking about atomic emission or using that spectropolarimeter up there that I won't let anyone touch. So we want absorption to occur when doing AA spectroscopy. So why do we have a flame? That's a tough question.
Molecules in their excited state?
Well, we're doing absorption spectroscopy, though, so we don't care if we get a little bit into the excited state. What I think that the word really helps me is the flame is our atomizer. I don't know if that's the best word for this, but we're doing what type of spectroscopy? Atomic absorption. So we have to have atoms. So you could have, and we always have these solutions that we're trying to suck up that little tube into our AA. Well, there's atoms in there, but it's solvated. And there's no way you can talk about there's an atom there. When we say a gaseous atom, we need an atom in free space, nothing else, right? That's it. You have a gaseous atom. Well, that's not what you have here. So that's the whole purpose of the flame. The flame is to get those gaseous atoms. Okay. Yeah, I haven't finished the story yet, but this is only part A. We'll finish the story next class period.
So does it like burn up the solvent? Just like it isolates the molecules you want?
Pretty much. And then it's not molecules either. It's atoms, right? Because molecules aren't going to work, and we're going to talk about why later, really. The whole reason why this is spectroscopic technique allows you to quantify and qualify, in other words, figure out the amount and figure out what it is due to this line spectra. Molecules don't give you that. And we're going to talk about why that's a big problem, probably in the next class period. But This is all atoms. Atomic absorption spectroscopy. Atomic emission spectroscopy. The point is atomic spectroscopy. So it has to be with atoms. So we're going to be using a flame to get those atoms. Yeah, and burn off the solvent or boil it off. Burn off, but it almost means like you're having a reaction changing state. So I'd say boil it off. Right? Make everything atoms, make everything gaseous, and then only the atoms that we're interested in are going to absorb those narrow lines. Okay. And there might be interference, and we'll talk about that again next class period. So how does our AA introduce the sample into the flame? We've got this nebulizer assembly. Here it is. Okay. So where in this picture is that little white tube that you, little white Teflon tube that you insert into your sample, and then it sucks it up? Yeah, there it is, sample capillary. There's our white tube. That's what's sucking it up. So you've got a beaker here or something, and your solution is there, and it's sucking it up. Okay, and then it's sucking up into here, right? And there's a nebulizer. So what is a nebulizer doing? It's just whatever you're sucking it up, there's this. Oh. Let's show you here. See if I can get this going again. Okay. So there's my flame. And here's my sample. I want to look for sodium. So one thing I could do, all right? It's not very efficient though, right? I mean, you saw a little bit of orange, and almost everything went on the table. Right, Andy? So what would be a better way to introduce a sample? Can you think of a way? I could do it a little bit, yeah, stick something in there. That works pretty good. Then you could, you'd have to stick this metal loop into the sample and put it in there. What I was thinking, I was hoping someone would say something like this, right? You could, instead of dumping it in there like this or like this, make the droplets even smaller, right? If the droplets are even smaller, that's what this little guy's doing. Get a little tiny dinky droplet. All right, look at that. Works great. Okay, so that's pretty much, except let's make the droplets, these droplets are still huge. Let's make the droplets even smaller. So that's what this nebulizer is doing. It's an ultrasonic crystal, and it's just vibrating, and it's making ultrasonic. It's making a lot of this liquid, it's vaporizing into really small droplets. But pretty much everything ends up going down to waste, right? Only the finest droplets make it through this baffle and stuff. But this whole thing is getting sucked up into the flame. Okay? So the flame is drawing it up there. How is the flame, well, does that make sense so far? Okay. So the sample's getting only the smallest droplets. The sample gets pulled in and gets nebulized. Most of it ends up going to waste. Only the smallest droplets make it through the flow spoiler, right? These baffles, and gets carried up into the flame and does its thing. Okay. And we'll talk about how it draws it in a bit, but let's finish this question. Flashback. Flashback is explosion. So you've got a volatile mess of a bomb down here. You've got these volatile gases that can, ignite in an enclosed area. So if that flame could creep down and get into here, you'd have an explosion. And they call that flashback. So where does flashback occur? In here, right? Because this is the enclosed area. Yeah, that's how I'd answer that question. We're supposed to have all these safety features on our AA that stops flashback. I say supposed to because they've never been tested. Who wants to test that? I think what they're talking about is more like the O-ring nature of the thing. In other words, if something explodes, they just pop off. I think it's nothing electronic, it's just a physical design. Okay, last question is, how does the stuff get drawn into the flame in the first place? It's the Bernoulli effect. It's the same question how planes fly. How does a plane fly? Anybody know? We're almost out of time. We got to answer this quick here. What's the shape of a wing? Flat on the bottom and curved on top. There's probably a little more shape to it. They have better shapes. But the point is that the wing, here's my wing, and it's going this way. Okay? So the little air molecules on top and bottom, which way do they have to travel further? On the top, they have to travel further, right? Because it's a curved surface. So if they're traveling further, are they traveling faster? Because the wing, it's the same amount of time, because the air doesn't move. So the air on top has to travel a farther distance in the same amount of time as the bottom ones. So it has to be going faster. Makes sense? These guys have to be going faster. And fast-moving air is low pressure. Fast-moving air is low pressure. So that means if you'd have high pressure here, you'd have low pressure here. So that means, whoa, you're buoyant. I don't think they use the word buoyant. They use the word lift. But it's the same idea. You're going to go up. So I'm going to take this rubber doohickey here, with a hole in it. I'm going to put it through here and blow on it. Right? So just picture what's happening. I'm going to blow as hard as I can to blow this onto the tabletop. Right? It should work, right? Blow really hard. But as I'm blowing hard, look where the air's going. Yeah, the air's blowing on this thing, but it's going to end up going straight across. Air down here is not moving. Air up here is moving. Lower pressure. The harder I blow, the more lift it's going to have. All right? Bernoulli effect. That's why the air gets sucked up here, because it's right. It's moving really fast through here, so it has a low pressure. Fast-moving air through here, so that means it has a low pressure. So it's just everything gets sucked right in there. The Bernoulli effect. So have a good day.